Well, I think that the science community has gotten over its shock and incredulity at the beginning, and now has developed, has evolved into a serious evaluation of whether these things are real or not. And in some cases, I believe it's well established that there indeed are effects. I think these
from Texas A&M on 7 chemical explanations of the Fleischmann-Pons effect. As I understand, the paper will be given by Dr. Bockris.
Yeah. Well, good afternoon. And I suppose that by now we've seen a good many people who've produced effects which show that sometimes, at any rate, and adventitiously, and when you do the right thing, it seems you get neutrons. There have been reports of a great deal of tritium, which apparently come now from 3 other labs, and sometimes, if you do the right thing, you get the heat. But we've not heard, except perhaps for the presentation of Professor Grozzi, any indication that there's a correlation between the neutrons and the heat. And indeed, right from the beginning, in the first days with Fleischmann and Pons, the stupendous 10 to the 9 discrepancy between using the neutrons to explain the heat has always militated against connecting the two up. And now that the neutron phenomenon become a little clearer, and qualitatively speaking, agreement between numerous people, it seems that the essence of the neutron phenomenon, is to come in bursts which last for a few hours, as little as 1 hour, as much as 5, a few hours, and go away again. Now, in the Srinivasan, Appleby's Srinivasan calorimeter, which you heard about on the first day, there's an extremely clear indication that the heat switches on after tens of hours, 20, 30 hours of electrolysis, pre-charged, of course, before that, and then, and this is my point, stays constant, very constant, for more than 100 hours. In fact, it may be much more than 100 hours, but because Appleby and Srinivasan have just the one calorimeter, which works with just the one electrode, they usually stop it after 100 hours in order to do change conditions and so forth. Well, of course, that's utterly and completely different qualitatively from the neutron phenomenon and its crazy behavior. It's up and down, so on and so forth. Furthermore, the neutrons shut off when you increase the current density, totally against any intuitive concept of the phenomenon, whereas the heat does react somewhat to the current density, although it's true that you can increase the current density without changing the heat very much. All this being the case, then, is the preliminary to what I'm going to talk about, which is an attempt made by several of my co-workers to work out several very simple schemes of chemical causes of this heat, and to see whether we can make it, as it were, in respect to the amounts of heat which we would have to explain to reach the observations. Now, I have therefore to state what I'm going to assume are the observations, and of course, were I to compare it with the observations in great detail, that would be complicated, so I'm just going to take 10 watts per cc as the sort of heat that is observed when it is observed, and that covers Srinivasan results, which go between about 7 and 27 watts per cc. Pons was talking about 26. Several other people's results come to tens, and therefore I'm being a little conservative when I just take 10 watts per cc. In other words, I'm going to look at various schemes, and I'm saying, can this scheme give me anything like 10 watts per cc, or 1 watt per cc, or something in the ballpark anyway? Well, the first one I'm going to consider is the much talked about chemical recombination of deuterium and oxygen, and the gas phase recombination. There are 3 versions of this calculation I'm going to talk about. The one is the simplest one, the most naive one, and the one which most chemists know won't happen. Namely, the deuterium and oxygen go up into the gas phase, and of course they collide, But most chemists realize and know from many, many experiments, which are very classical, that except at high temperatures, there's a negligible recombination between hydrogen and oxygen in the gas phase in the absence of any catalyst or increase in temperature. So it's very unlikely that that will happen. Nevertheless, we worked it out in the following way. Let's assume it does happen. Let's assume it happens to the full extent that we can. By the way, several of the figures haven't been corrected for the isotopic ratios because these are all very rough calculations. So 68 is the figure for hydrogen-oxygen recombination. And if you take 100% recombination, and you assume it's going on all the time, and you're comparing your heat with E minus 1.54 times I, as very carefully explained and very well explained earlier on in the afternoon, then you would get a great deal. You would get about 18 watts per cc. I've had to assume definite electrodes to make these calculations, and I've assumed electrodes of 4 millimeters in diameter and 10 centimeters in length. But I've worked it all out again in watts per cc. So if you did have that recombination, it would add up to a great deal. However, there have been many measurements at Texas A&M of that recombination. I don't mean perhaps 10, but I mean at least 6, and by the 3 different groups. Everyone has done it and done it again, and no one has been able to detect any recombination. However, it's true that we haven't got a very super accurate way of doing it. We do it in a rather high school manner, I must admit, and therefore we are not claiming that it's better than perhaps 1 or 2%. So let's say that at least 98% doesn't recombine, and that automatically knocks that one out totally, because of course you'd have to multiply by a 50th on 18 and get less than half a watt. So that ordinary recombination, as I think intuitively clear, doesn't apply. Now the next one, which is a version of the same thing, it's a recombination one, but a little more subtle, is, I think, a danger. And it's what I call the Freysa pump, F-R-E-Y-S-A. I call it the Freysa pump because Gerhard Freysa gave a paper on this at Los Angeles. He was very upset about the discussions being made about the heat, and he vigorously maintained that it was all to do with the fact that as the electrolysis goes on, and perhaps during the night, if you don't have dedicated research students who pop in and out and look at it all night long, the D2O goes down below the top of the palladium electrode, and so you've got this D2 and O2 coming up. You've got lots of O2 around it, and there's the pump. The D goes in. It's being compressed hard in here with the overpotential of the surface reaction. But if it gets up here, a half, so to speak, it's free of the surface reaction, the overpotential, and it will start to diffuse out, and then it's in contact with 1/3 of an atmosphere of oxygen, and what would happen then? Well, we calculated that. The calculation on this one was a little more complicated, a little more sophisticated, and I'm not going to give it to you all. It involves assumptions about the diffusion coefficient of hydrogen through the palladium. It involves assumptions about spherical diffusion. In all cases, you bent over backwards to increase the effect. For example, we've taken the DPD ratio as 3, which is absurdly high, but nevertheless, it's the very maximum we could possibly justify, and all will go to increase the effect. We've also taken into account the possibilities of surface films, which would slow down the oxygen diffusion to it, etc. And depending upon the surface films, we assume we kind of get results which go down to 0 or negligible totally. And with the assumption of a 1 micron film of water, the heat then comes to 0.2 watts per cc. It's not watts per square centimeter, watts per cc. Now, that one we can also look at experimentally, because Charles Martin at Texas A&M did a calculation of the following, or not a calculation, an experiment of the following kind. He just purposely took his electrode and exposed it. He did runs. He's got quite a good calorimeter, not associated with Ken Marsh of the Thermodynamic Research Center at Texas A&M, not as good as the one that Shafferby and Srinivasan have got. It's a good one. And he took it out, exposed it, he took a quarter of the electrode out of the solution and found not a jot difference. Didn't make any effect at all. So my calculation was over-conservative, and the answer is there is nothing of this kind. Now, coming back again to the Srinivasan results, remember that we have in the Srinivasan results platinum in water, and of course there's absolutely no reason, if there were any recombination going on, it wouldn't show up when hydrogen and oxygen come off from platinum and water, as well as D2 and O2 coming off in the other experiments. And with the platinum water experiment, Srinivasan gets absolutely on the line of E minus 1.54 times I. He's indistinguishably exactly on the line. And that, I think, crosses out that one. Now, Wayne Goodman at Texas A&M, chemist in the room will know his name, well-known kineticist, suggested the following. He said, well, maybe there's no recombination of the gas phase, we know that, and this idea of the Freiser pump doesn't work, but perhaps it is that the constant injection of bubbles of oxygen against the palladium electrode, because the cathode and anode are pretty near together, and there's very, very vigorous evolution at 1 amp per square centimeter, perhaps the bubbles momentarily touch the electrode and give a direct palladium-oxygen contact. And there being zillions and zillions and zillions of bubbles, even if the contact lasts for a nanosecond, perhaps it would give something. And that's indeed a tenable hypothesis. And what I've done with that one is I haven't tried to calculate the kinetics of the collision of the bubbles, which would be a paper, I would think at least, but I've taken the 2% recombination maximum, which we think we can allow ourselves, and I said that even if Wayne Goodman's suggestion is correct, it can't be more than 2%, and on that then I get the excess heat 0.3 watts per cc. In all these calculations there is a time element, a very, very important one, as will come out more in a moment with some of the other calculations. I have assumed 100 hours. There's plenty of evidence that it goes on this effect when you get it for 100 hours, and much, much more. Of course, Fleischmann and Pons have talked about thousands of hours, but Srinivasan, whose data I know well, has got at least 100, and therefore I feel I'm secure in taking 100 hours for comparisons with static quantities. Well, now the next one is to assume that, this is rather an odd one, perhaps you think it's unjustified, but to assume that the alpha to beta transition of palladium and somehow wasn't complete, and that's been going on all the time, and that it's been going on all the time the electrolysis is going on. Could that be a source of the heat? I think most of you will think this is a fairly far out one and rather unlikely, and indeed it may be, but it doesn't really matter because, as you see, if you assume it's going on over 100 hours, I've carelessly just assumed it was 1 eV because I couldn't find a value for it. It's obviously of that order of magnitude. If it's 3 eV or 0.3 eV, it doesn't really make any difference because it gives an absolutely negligible contribution to 10 watts per cc. Well, the next one was to say, and this has also already been done by one person this afternoon, to say what would happen if you take into account the formation of palladium deuteride. A lot of people have said this. They've said, what's happened to all that charging? You do all that charging, and surely you must be putting some energy into it, and it gets stored in the hydride, doesn't it? So let's look at that one. Here I had to assume a lot of things. The main thing I had to assume was the DPD ratios, and I've really gone far out on this, assuming 0.7, 1, 3, and 6. Let me just say why I chose that apparently absurd value of 6 as an extreme. Of course, it's good to have an extreme because the effect is increased if I take that. It's not absolutely absurd. There's a little bit of evidence for it, and it comes from the work of an electrochemist called Stimming, who reported at Los Angeles that he had detected a value of 6. But how he did it was rather doubtful, and I don't think I want to describe it. But at any rate, he's a very seriously taken electrochemist, so we had to assume that it could be true, and I've done that too. Well, of course, you have to make assumptions about bond strengths and so on, but as every chemist knows, bond strengths don't vary by more than 3 or 4 times, and it all comes out to be something negligible. What does it come out to be? It comes out to be 0.6 watts if you really go up to the 6. If you go to the more reasonable 0.7, it's only 0.07 watts per cc. Well, then there's one which says, lithium alloy is formed, and that's not been taken into account in anything. And therefore, if that's forming all the time, maybe that's the heat that we're looking for. Well, I've been talking to people at this meeting, and it seems that there are contrary opinions and dispute about lithium alloy formation. Some people have used XPS, don't find it at all. We unfortunately haven't got to that yet. We have plans for it, which will soon be accomplished, but the next week or two, we haven't looked for it. But there are other people who say that it does alloy, and they have found it. In electrochemistry, the alloying of lithium with platinum is well known, and it takes place to a great extent. Furthermore, the lithium doesn't only diffuse in, it positively reacts, and it reacts very quickly. So I've gone the whole hog, and I've assumed that the whole darned electrode is a lithium-palladium alloy after 100 hours, which is an extremely unlikely but conservative assumption. And then I've taken various bond strengths from a book on bond strengths, and I've come out with palladium-lithium bond strength, and please don't argue that one with me and tell me it's really 52 or something, because it doesn't make any difference. It can be halved or doubled. It's all going to be much less than 0.1 per cc in watts if you take it over 100 hours. Well, now comes a really strange one, and this strange one comes from a paper which has very recently been published by none other than Linus Pauling. I think few of you know about this because it came out in Nature of May the 11th, which probably isn't generally available here. I got it by fax from London. I'm going to read you the essential part of his note. It's a one-column note. It says the following. He argues to start with, quoting his own book, of course, I also pointed out that the need for the metallic orbital for stability explains the fact that palladium is saturated with hydrogen at the composition PD80.7. Introduction of additional hydrogen would lead to instability because of the loss of resonance energy when the metallic orbital is not available. I judge that under the conditions of the electrolysis experiments of Fleischmann and Pons, deuterons beyond this limit are forced into the palladium cathode, ultimately forming the unstable higher deuteride. Later, after the beginning of electrolysis, this unstable deuteride might begin to decompose, either slowly, resulting in an increased liberation of heat, or explosively, as Fleischmann and Pons observed when a 1 centimeter cube of the deuterated palladium disappeared. Well, Pauling, as every chemist knows in the room, is certainly the most famous chemist in the world. One minute. And his word, in spite of the fact that he retired 25 years ago, is still very active in his own research institute. His word must be taken as something seriously. So we tried to look at this at Texas A&M, but frankly we found it difficult to understand because of the fact that, of course, we are all the time pushing D in there, and we're under high current density conditions. The D is going to be increasing or getting to a limit, and certainly the idea of it dissociating and coming out is very difficult to, in my opinion, to understand. But nevertheless, we plowed on. We took the bond strengths of PDD2, and then we looked at a hypothetical lattice of PDD2, and we did all sorts of things to get numbers which might up the value. But the extreme we could get with that one was 0.7 watts per cc, with the doubt as to whether it's qualitatively a goer. Well, the chairman is telling me I must stop, and therefore I will put this last one on, which summarizes the various calculations. And I think I can say that the only one that leaves me with some fear is recombination, perhaps. And we must say, and Dr. Appleby said this on the first day, that the Texas A&M, many recombination experiments were all done outside the Srinivasan calorimeter. They were not done from inside it, and therefore there is still just a tiny, tiny thing about that, which we're of course going to get right very soon. So it can be summarized by saying we can't get it up very far. Of course, it's obviously not likely that all those effects would occur at the same time. 0.1 watts, that's the summary of the paper.
Thank you. The paper is open for discussion.
Louis Muga, University of Florida. Another possible explanation, I believe, would be alternate side reaction. Another possible explanation, I believe, would be alternate side reactions at the anode. For example, production of peroxide, peroxycarbonates, things of that sort. And rigorous exclusion of these must be established. The products could drift in solution and subsequently react in the vicinity or at the surface of the cathode, releasing heat. If additionally then one adds back the recombination heat from stoichiometric release of oxygen, as per Faraday's laws, one is bound to report excess heat. So the deficiency of O2 at the anode, a deficiency, would indicate such side reactions. We have run two identical cells in series, electrical series, one in D2SO4 and the other in LiOD with a platinum wire anode. Clearly, just by visual observation, far less oxygen is evolved in the base solution as opposed to the acid, quite a bit. We are setting up now to do quantitative analysis to confirm this qualitative observation.
Well, I think I comment on that this way. Is that your point? May I comment?
Well, one more point is that open...
I'm sorry, I'll have to interrupt. This period is for short questions rather than presentations. Okay. So we'll have the chairman answer.
Very briefly, electrochemists would say that the oxygen evolution is always less in the alkali because the overvoltage at the anode is higher, much higher. And the other thing is that we did think of this explanation, not quite in the same context as you wanted it, but we were worried about peroxide effects on the cathode. So we tested the cell with a well-known test for H2O2. Within the limits of that test, which is 10 to the minus 6 moles per liter, we couldn't find the H2O2. Now, the whole problem of H2O2 at anodes in electrochemistry is a well-worn one. It's one in which I've worked, and indeed it does get produced. But it usually gets subsumed again in a second reaction on the anode. And of course, it always goes to water. So the net would be 0. In the occasion when electrodes do give off H2O2 net, we call it the two-electron transfer reaction, and then you don't get the Faradaic yield. And so you wouldn't get the Faradaic yield we've been getting, which of course is based on the assumption there's no H2O2. So there's fair evidence. Dr. Huggins, of course, suggested that, or pointed out there were any corrosion reactions, and that's really the same as what you're talking about, took place, then indeed you would get some extra heat. But one thing I think one would say, and I see Dr. Srinivasan put his hand up there, all this would again come in to the Srinivasan experiment of H2 and O2 on platinum in water. That would surely give you the same effect, and it doesn't.
Thomas, Institute Ruđer Bošković, Zagreb, Yugoslavia. I would like to ask you...
Please stand up and identify.
I would like to ask you about possibility of Wigner effects in palladium.
Well, can you spell out what the Wigner effect is, that I might be able to comment on it?
That is, you see, when you have radiation damage, for example, in graphite somewhere, and when you heat up, after that, you have some forbidden transition. This happened in this scale, you remember this.
Well, I think that's fairly easily dealt with those. Yes, the only way that you could bring that in would be if the overpotential of deuterium on palladium is sufficiently different than the overpotential of hydrogen on palladium to make the difference. That's to say, Srinivasan et al. Find that the water effects, that the palladium in water gives nothing. So it'd be very funny if the Wegener effect switched on when you turned to deuterium. I mean, that would be a bit far out, wouldn't it? I think that it's unlikely, therefore.
I think we'll have to move on. Thank you. The next paper is Evidence Against Condensed Matter Fusion Induced by Cosmic Ray Muons. This is a communication from Nagamine, Matsuzaki, Ishida, Sakamoto, Watanabe, Iwasaki, Miyake, Nishiyama, Kurihara, Torikai, Suzuki, Isagawa, and Kondo from the University of Tokyo. The paper will be presented by Mr. Nagamine.
I'd like to talk to our recent experiment, which demonstrating evidence against condensed matter fusion induced by cosmic ray muons. Work was done by University of Tokyo RIKEN KEK collaboration. This work was motivated by the paper written by Ivanhoe group and also many similar questions from many people in many fields. And at the same time, this work was also motivated by the considering possible role of negative muon for enhanced condensed matter fusion. The argument done by Livermore group and also many other people's arguments should have based upon assumptions, following three assumptions, which is somewhat against common sense of our muon physicists. First of all, they assumed enhanced atomic capture to deuterium by considering complete shielding of d electron around palladium. This assumption is against the well-known so-called zero or Fermi-Torah law, which is applicable to almost all the muon capture in compounds, which predicts deuteron and palladium atomic capture ratio is proportional to Z, namely 1 to 46. And also, they haven't considered at all about the mu minus transfer from D to palladium. We know in compound, the neutral mu D goes to the palladium quite rapidly. The phenomenological experimental number is predicting 5 times 10 to the 11 sec inverse. And also, we need extraordinary highly enhanced DD mu muon catalyst fusion in palladium deuterium system. We need somewhat 700 muon catalyst fusion per mu minus, which is also against the well-known mu CF data on DD mu system, which predicts somewhat around 0.2 per mu minus. The summing up all these assumptions, they obtain 0.1 neutron per sec, which is consistent with BIU measurement, considering cosmic ray intensity stopping in 20 gram or 35 gram titanium or palladium. So in order to confirm, check all these assumptions, we started our experiment and tried to measure muon catalyst fusion related observables by using intense high quality accelerator muons. Intensity is certainly 10 to the 10th or more higher intensity with high quality. Experimental arrangement is exactly the same as those we used for recent successful experiment on the direct X-ray measurement on alpha sticking probability in high density, high tritium concentration D2T2 muon catalysis fusion. This is our experimental area located at KEK. The 500 MeV proton synchrotron provides the beam to the production target, and pion is produced and injected into superconducting solenoid decay section and extracted into the experimental area. The uniqueness of this facility is we have pulsed beam with high quality time characteristic, which is quite important for the low background measurement for the mu decay and atomic capture determination. At the end of the muon channel, we installed this setup. The muon is coming to the target area. At this moment, it's written on the D2T2 target, but it will be placed to the palladium deuterium system. And we placed all the target under high longitudinal magnetic field of 3.5 Tesla. It has superconducting coil winding like this, and because of this high field, longitudinal field, first of all, muon is focused into the small target, and also all the mu decay background, which may hit to the either Siri X-ray detector or neutron detector, stays away from these counters. And here we install mu decay counters in order to measure atomic capture ratio. This is a picture of the setup. This side is close to the human body's head. Although it is not related to this conference, but as a demonstration of the sound performance of the setup, I'd like to show you the neutron time spectrum, and gamma dispersion spectrum, neutron energy spectrum, and also recently observed X-ray peak demonstrating first direct observation of the alpha sticking probability. So let us come back to the condensed matter fusion. The observables in our experiment is summarized here. First of all, decay electron time spectrum with reference to beam pulse, which is useful for the so-called lifetime method for the atomic capture ratio determination. When muon is captured to deuterium, the decay time constant becomes 2.2 microsecond, while when it is captured to palladium, it becomes 100 nanosecond. Then, in order to search for the muon-induced fusion neutrons, we measured time spectrum, energy spectrum, and gamma discrimination time spectrum for the delayed 2.5 MeV neutrons. And also, in order to measure the fusion-related charged particle effect to produce the electronic palladium X-ray, we measured timing and energy of the delayed photon emission. Samples we adopted is mainly done by the KEK cold fusion group. Is summarized here. The palladium deuterium sample, we know this size, and we loaded deuterium for 10 hours and up to the D per palladium ratio or 0.6. This deuterium concentration was confirmed by not only weight measurement but also neutron scattering. And at the same time, we installed the small electrolysis electrochemical cell into our target area exposed to the muon beam in this geometry. As a control, we adopted a palladium sample without any deuterium. This is a picture of the target area when we used the small electrochemical cell exposed to the muon beam. Now let me show you the result. This is the result of the mu decay presented in the logarithmic scale for the pure palladium. This this is a time. This short time component belongs to the mu minus stop to the palladium. This is a background. And when we change to the palladium deuterium in open air, placed in open air, the data is just the same. So mainly the muon is captured to the palladium. And when we install the palladium deuterium system in D2O, there is significant difference. Like this long component appeared, but unfortunately this is not palladium, and this is not muon captured to deuterium. And after the analysis, the lifetime of this component is known to be 1.8 microsecond, not 2.2 microsecond. In order to show you the result more clearly, this is a summary. This is not 2.2 microsecond lifetime, but 1.795 microsecond lifetime. This is mainly due to mu minus stopping in D2O. Mu minus D convert to the mu minus O. Eventually, all the stopping event in D2O gives us this lifetime of the signal. After making many lifetime component analysis of this lifetime spectrum, we concluded sorry, this is inverse. Mu minus palladium to the mu minus this is correct, sorry. Mu minus D to the mu minus palladium atomic capture ratio is below 3.3%. Then we switch to the search for fusion neutrons. This is L gamma discrimination, and this is the neutron time spectrum, or the mainly for the neutron events related to the palladium. And this is delayed neutron energy spectrum for the pure palladium, and this is delayed neutron for the palladium D in D2O, and essentially no change, particularly around 2.5 MeV peak. After analyzing this data, we concluded the fusion neutron yield is below 1.2%, 1.2, sorry, 0.012 per mu minus. The X-ray yield, this is again the X-ray yield at the time of the muon beam arrival. Because of the small impurity of the muon beam, we have X-ray peak to the palladium and platinum. But when we make a delay after 240 nanoseconds, there is no significant peak at all, demonstrating no significant charged particle emission from our system. So here is a summary of our experimental result. Small atomic capture to D versus palladium, and or we cannot discriminate two possibilities, and or fast transfer to palladium. And also small fusion rate, and known from the neutron intensity and also X-ray data. And here's the conclusion. Cosmic ray induced DD mu muon catalyst fusion rate is very small compared to the Livermore people's estimation. We must put this number. First, atomic capture times transfer rate is this number, and muon catalyst fusion is this number. Then the 10 to the minus 6 neutron per sec is expected for cosmic ray induced DD mu CF rate. So the observed neutron fusion neutrons from palladium deuterium system therefore should be due to something else, hopefully nuclear fusion in condensed matter. But at this stage, at this point, I'd like to mention one possibility which probably nobody has already mentioned at all. This is shown here. Possible role of negative muon to enhance cold fusion. Now we know even if we have fully loaded palladium and deuterium and palladium system, all the muon is eventually goes to palladium, initial atomic capture and also transfer from mu-D to palladium eventually produces muonic X-ray emission, which may cause the palladium recoil. The recoil energy is somewhat around 100 electron volt. Therefore, this muonic X-ray recoil may induce vacancies at palladium sites, which may enhance formation of DD pair in vacancy. Of course, many studies should be done. Therefore, if this is true, we must seriously consider another cosmic ray effect on this system. So that's my talk. Thank you very much.
Thank you. Are there questions on this paper?
I think you're doing a very important experiment, but I would really like to see the D to palladium ratio be at least 0.7. I don't believe anybody is proposing that any events occur at a PD D 0.6. And since your experiment is so important, it would really be nice to see one at a higher loading.
I see.
Any other questions? Okay, we'll then go on to the last paper of the afternoon session, Study of Energetic Charged Particles from Thin Deuterated Palladium Foils Subject to High Current Densities by Cecil, Ferg, Furtak, Mader, McNeil, and Williamson from the Colorado School of Mines. Mr. Cecil?
First, I have to apologize for standing up before you without a tie. I didn't think I was giving an oral presentation, and when I was told I was giving one, I decided to go to one of these little boutique shops around town and try to buy a tie, for a nice one for maybe $8 or $10, and the cheapest tie I could find was $42.50. A number of groups here have sought to look at charged particles from charged palladium targets. And the reason for doing that is very important. If you take the initial reports of high levels of heat compared to neutron and tritium production, and if you assume that it's some sort of two-body nuclear reaction as opposed to a collective effect, then this heat is going to come out in the form of charged particles. If you assume that the energies of the charged particles are in the few MeV to 10 MeV range, then you're necessarily limited to thin foils. We chose, rather than an electrolysis method or a gas loading method, as others have done, to use a deuterium beam to load the foil. And the reason for this is because you know the approximate range and you can get a good handle on the stoichiometry. So let me just real quickly summarize what we did. Target was prepared, it was deuterated with the beam, energy spectra were measured, and control spectra were also measured. The target was prepared by the evaporation method at the Solar Energy Research Institute in Golden, and consisted of about 1 square centimeter wide foil by 1.5 microns thick. It was on a 3-micron moly backing, which again was on a thick alumina backing. The reason for the insulating substrate of aluminum was we wanted to run current through it, and we wanted to make sure the current went through the actual targets. So between the 3 microns moly and 1.5 microns palladium, about 2/3 of the current that was run through here, 1/3 went through the palladium. In addition, a very thin layer, 0.05 microns of silver, was splashed on top. This is to optimize the loading on the assumption that some of the implanted deuterium without a surface coating might actually diffuse through the surface. The geometry of the experiment is indicated here. The beam from the accelerator hits a target which is at around 45 degrees to the beam. A surface barrier, 1 millimeter surface barrier detector, 3/4 inch diameter aperture was located a few inches away, and in addition, the circuitry for running the current through the target was fed into the vacuum. The vacuum was around 2 × 10⁻⁷ torr. The surface barrier detector was used not only to look for reactions after the loading had taken place, but also to monitor the loading process. And this is done very easily because you instantly are making a deuterium target just from the beam that stops in there, and then the subsequent deuterons that come in along the beam give you scads of protons and tritons from the DD reaction. Again, since the foil is thin, since the range of the deuterons is on the order of 1 micron, you can do excellent back angle spectrometry on these charged particles. They lose very little energy coming, if they have an energy of an MeV or so, they lose very little energy going through 0.5 micron of metal. The deuteration process is then monitored by just looking at the count rate for the protons made from the DD reaction during the bombardment. And this occurred at around 30 microamps of current over a 36-hour period, at which point you put in about 3.5 coulombs of deuterons, which corresponds to just about as many, in fact a little bit more deuterons than there are palladium atoms. And the fact that it leveled off indicated that whatever the stoichiometry was, it was optimized at that point. One thing that surprised me was this was done, as you see, several weeks ago, and the measurements were then carried out over the course of the following few weeks, and I expected to see a slow decrease in this level. And you can check that again, since the since the measurements, the non-beam measurements, the beam-off measurements are made in the same geometry. If you ever want to go back and check the deuterium loading of your target, you just kind of switch to a different group in your analyzer, turn the beam back on for about 5 or 6 seconds, and you see the same level that you stopped with, plus or minus 20% kind of flopping around. So I was a little bit surprised that maybe the silver on the coating was responsible for that. The spectra that you see during the beam bombardment is just a lovely spectrum. You see 2 peaks, 3 MeV proton, broadened 1 MeV triton. There's a foil on the surface of the aperture to prevent elastically scattered deuterons from creaming your detector, and that foil is thick enough to prevent seeing the 800 kilovolt helium-3. So you see 2 lines here instead of 3. Now, this is what it looks like with the beam off. What does it look like with the beam I'm sorry, this is with the beam on. What does it look like with the beam off? This spectrum was taken, as I said, in just a few seconds. A 19-hour spectrum with the beam off indicated this. This large feature here is just the fact that the detector was run warm, and it's just thermionic effect from electrons that are up in the silicon conduction band. The cutoff here is instrumental. If you compare the two spectra where the energy calibration is the same, there's a very small suggestion of a peak at 3 MeV. This is at the level of statistics. This is maybe 1, 2 sigma. We continued to run on this, and it was not reproducible. What was reproducible, however, was a feature, a broader feature out at an energy of around 5 MeV. And this persisted at different currents and over long periods of time. However, as I said, it was broad, so the data were grouped in wider bins. This is the beam-on spectrum, protons, 3 MeV protons, 1 MeV tritons, for this broader energy binning. So a 90-hour spectrum taken with the beam off is shown here. The same instrumental cutoff around 2 MeV, and the feature that was out at the right-hand channel in the previous one is now here. The statistics on this are that there are 30 plus or minus 7 counts after the background is taken off. That's about a little bit more than 4 sigma. This is just 2 of the runs. There was another short run with the detector cooled, so the statistics are actually a little bit better. It's important to do 2 control experiments. The 2 control experiments I did was to leave the target exactly as is, take a long count with the current, this is now the battery current, through the foil turned off. Same deuterated target, no current, no counts statistically significant out here in this channel. Another very important control that we had to do was to take a non-deuterated target, run current through it on the possibility that we were somehow picking up a signal from the current. This was a DC current, maybe fluctuations were sneaking into the preamplifier. Again, 50-hour background, 50-hour count, nothing above background. So the yield as a function of battery current through the target is shown here, linear up to 1 milliamp, and then the single point here would have been decisive had it been continually increasing, but appeared to drop off. I should add, and this is emphasized in the abstract, that these are very high current densities. The target is, and let me go back to the original sketch of what the target looked like. This 1 milliamp of, these milliamps of current are determined by a 24-volt output on a NIM bin and then a variable resistor. 1 milliamp of current going through here corresponds to 2 amps per square centimeter, since you have this thin, flat foil, and the current has to go from here to here. Okay, so the maximum current that we were running through was higher than anything I've seen at this conference in terms of amps per square centimeter. That is the statement of the experimental results. To within 4 sigma, there is a particle group at 5 MeV, which correlates with current and correlates with deuteration. Now, if you allow me some what has to be given the award for the most mindless speculation of the conference, let me speculate as to the source of these. The Q values line up pretty nicely with the dpq values. This is not D plus P, has been talked about many times. It's a deuteron on a palladium nucleus, proton coming out. Exothermic reaction as you go over the 4 or 5 various stable isotopes of palladium from 102 to 111, something like that. The Q values, most of them around 5 MeV. One of them's a little bit higher. This explains one nice thing to me, and that is why I don't have a narrow line. As we saw back here, even with large solid angle detector, non-cooled, you still have pretty good resolution. Not great resolution, good resolution. Why does this line that we see at 5 MeV come out so broad? If it were a superposition of several lines, the intrinsic experimental resolution would be washed out. Well, the only thing wrong with having a DP reaction on palladium is the Coulomb barrier. If you just do a simple gamma penetration factor, you get 10 to the minus 4,000. Okay, try punching that into your calculator. Smoke will start coming out the sides. It just refuses to calculate 10 to the minus 4,000. So we looked at some of these screening calculations similar to what Jerry Hale was talking about, and there have been a number of articles in the literature on screening on the very light isotopes. And this theoretical work was done by my colleague Jim McNeil, who's just a fine theoretician, and he's gotten very excited about this stuff at low energies, and so it's been fun working with him on this. He reproduced the screen potential that was discussed yesterday, and I couldn't find a picture of it, but my recollection is it was something like this, where you have, without any screening, you have a simple Coulomb potential. With screening, you get a minimum around 1 angstrom. Took the same code and switched the DD screening to palladium deuterium screening and got a very deep potential well. This is minus 300 volts at an absurdly small radius. As I said, I'm an experimentalist, and my portion of it was over 10 minutes ago, and now this is just mindlessness. This allows or suggests the possibility of very close approach of the deuterium and the palladium. You would still have a formidable Coulomb barrier to penetrate through, but it goes from 10 to the minus 4,000 to 10 to the minus 368. So in terms of improvement, it's the best thing we've ever heard, right? 3,275 in the exponent. So I don't know. That's as they're talking to some of you that are good people. Yes, sir. There's a lot of problems with this. But the thing that has to be taken into account, that has not been taken into account, is something I referred to in a question this morning, and that is the internal structure of the deuteron, where the deuteron can get stretched by very strong electric fields. And again, there have been some very interesting calculations of this recently, and everybody says it's a non-effect. You can't affect nuclear reactions. There's an effect seen in the DD reaction, and there's an effect that we saw in the D lithium-6 reaction a few years ago, where we measured the ratio of the DN to the DP and saw a 30% effect at an energy of 50 kilovolts. The picture goes way back. It's called Oppenheimer-Phillips effect. The first paper was written by Oppenheimer and Phillips in 1938, and the idea is that in a strong electric field, the neutron and proton get stretched out, so the neutron can get in to make a DP reaction without the proton having to penetrate through some enormous Coulomb barrier. It takes a big electric field to do that. But wouldn't that solve a lot of problems? I mean, if you could have DP reactions with just charged particles coming out, no neutrons, no gammas, no nothing, just lots of heat. Okay? Now, is this observable? Are the consequences of this observable? Well, one of the things I got to do is to improve my detector setup and maybe get a two-particle sandwich so I can do particle identification and see if in fact they're really protons. The other thing we can do, and this is not an invitation to grand larceny, is if we could get a hold of one of these rods that had been working furiously for a long time, is do a decomposition of it and look at the isotopes that are left. And there are two isotopes of palladium, 111 and 109. 111 has a half-life of 13 hours, 109 has a half-life of 10 to 6 years. You'd see those isotopes in one of these cells that has been producing lots of heat for a long time, if in fact the source of that heat were the DP reactions on palladium. So I certainly have some work to do, and it's nice to think that this is, even though it's a crazy hypothesis, it's testable. Okay, that's all I have to say.
Thank you. Questions?
Thank you. James Airden, Naval Research Lab. I've talked before. I just wanted to note that at that, if you do have 30 counts over 90 hours, that's not a Pons-Fleischmann reaction.
Oh, I should have emphasized that. Can I give the numbers on what that is? I wrote them down and meant to tell them. I'm interrupting your question, but can I give those numbers?
Okay, sure.
Great. 30 counts over 90 hours is 10 to minus 4 counts per second. Given the A over 4 pi r squared of the detector, that's 10 to minus 2 reactions per second. Since it's a thin foil, that's around 60 reactions per cubic centimeter per second. Assuming it would be a bulk effect. If this is a surface effect, then everybody here has to go back and reevaluate the volume that they're dividing by. That count corresponds to 5 times 10 to minus watts per cubic centimeter, 5 times 10 to minus 10 watts per cubic centimeter, and corresponds to 2 times 10 to minus 1 reactions per DD pair. Thank you for reminding me to give those numbers.
No problem.
Is that all? Oh, come on, say something else. Okay.
We had done the same experiment in a similar, not exactly the same, but a similar experiment, and found nothing, but then the reaction rate is very, very small. So 30 counts in 90 hours, we do not go that long. But it is hard to find.
Schiffer, Argonne. I have a question and a comment. Question, how big was your foil that the current was passed through? What was area again?
1 square centimeter, 1 square centimeter area, and 1.5 microns thick.
And your beam spot was 1 millimeter?
Yeah, about the same. It was defocused, so you can spread the heating load out. About 1 square centimeter.
Comment is that I think the last 2 things you mentioned, the Oppenheimer-Felix process, I think is absolute nonsense. I don't want to explain it now, but I would like to explain it afterwards.
Okay.
And my neighbor says that so is the potential you showed with neutrons on palladium.
I'd love to see a good few body theory of that lithium-6 data. Nobody, I mean, Jerry Hale notwithstanding, I love the guy, and we're talking about stealing an entire cray to use it. I don't know how to do that, but that everybody says it's not an effect. This is a big effect.
Robert Perry, OSU. Since you brought up the T plus P reaction channel as a possibility of getting heat without getting neutrons, I can't help but mention the fact that even if you try to open up that, enhance that channel, and you need far more than 30%, of course, the high energy protons will still collide with the palladium atoms, as Bailey's calculated, and give you a large gamma ray signal. And it would be a very noticeable gamma ray signal. If I'm not mistaken, something like 1 proton and 10 to the 6th gives you a high energy gamma ray from the collision with the palladium and the excitation.
Okay.
At the milliwatt range of power, that gives you a quite observable.
Right. If you have a flux of a source of 10 to the 6 protons, 3 MeV protons in palladium, I would believe that you'd get some gamma ray background. That's a second order effect, but it would be big. Thank you.
Oppenheimer-Felix effect. You still need a mechanism for the deuteron to get close enough for that to take place? Do you have a mechanism?
That was the electron screening through that potential I showed that had a minimum at 0.2 angstroms.
Or the palladium electron?
No, the palladium deuteron.
Can you do that quantitatively?
The dashed line is the palladium deuteron potential.
How close? In terms of Fermi?
Oh, a large number of Fermis.
You need at least order of Fermis.
Right.
Thank you.
Norm Goldstein, Westinghouse R&D. What is the form of your film? Was it amorphous or was it?
It's initially crystalline. We've taken similar films and done X-ray diffraction on them, and after the same kind of bombardment, the X-ray diffraction gets a little sloppy, as if there's a certain fraction of amorphous, but there's still a dominant crystalline component even after the bombardment.
Okay, so that's what I was really leading up to. You don't think the radiation damage has a major effect then?
It might play a part.
All right. Thank you.
Ernst Stream from Oregon. I would recommend that you repeat that with a palladium 105 enriched target, because there's a highest positive Q value, and there you should get rid of this wide spectrum which really is coming from
That's a
palladium.
beautiful idea.
One more question.
Yes, Jan Rafelski, Arizona. We remember from our lectures lithium was an essential element in the Pons-Fleischmann type of experiment. The suggestion would be to implant lithium as well as deuterium and see if it doesn't enhance this presumed signal. If the Q value of lithium-6 DP reaction is 5 MeV
That's
by
right.
chance.
That's right.
Okay.
Yeah.
Well, thank you. We finish this afternoon session now. Let me announce that the poster session is still open. We do have an evening session at 7:30, and I think Dr. Brewer will make an announcement about this.
It's striking that you are making lithium in here.
Yeah, a couple of guidelines for the evening session. After discussing this with the program committee, we have decided on the following format. There will be no panel on the podium tonight. We will try to have a real discussion. We would like to ask the speakers of today and yesterday to gravitate towards the front part of the chairs. There will be a general microphone right available here up front, which the speakers can use upon answering questions from the audience. The audience can ask questions using the portable microphones, so there will be a lot of running around by people on the side, but that shouldn't bother you. Furthermore, I would prefer and strongly urge you to stick to questions. I don't want any monologues, philosophical points of view, or whatever from the audience. This stuff is too important from a scientific point of view, and we have many issues to discuss here. Furthermore, some technicalities here. Would like to, once again, to when you ask a question, to state your name, affiliation, and the speaker to which you would like the question addressed. And finally, since we want to end up before 2 years from now, I would propose, but this is somewhat flexible, that we limit the discussion on each issue to about 20 to 30 minutes. If we only stick to calorimetry, we can talk about for 2 days. If we only talk about radiation detection, the same story. But again, we have to see how that goes. Thank you.
Well, let's thank all the speakers of the afternoon and close the session.
Nuclear fusion, it's what powers the sun. Cold fusion, it creates headlines, and some say it could power Earth's future energy needs. Indeed, 2 months have passed since researchers called a press conference at the University of Utah to announce that they had demonstrated cold fusion. Controlled nuclear fusion, that is, at room temperature, achieved on a tabletop in an electrochemical cell, a test cell containing the metals palladium and platinum immersed in heavy water. Now, scientists from around the world are in Santa Fe, New Mexico. They've come to this, the oldest capital city in the country, a city tucked at the base of the Rocky Mountains and located in a state renowned for its unique blend of culture and cutting-edge science and technology. They're here for a special workshop, the Workshop on Cold Fusion Phenomena, an event sponsored by Los Alamos National Laboratory under the auspices of the U.S. Department of Energy. There are data and ideas to share and discuss, and research directions to chart and clarify. This satellite broadcast is available anywhere in the continental United States. Join us now as the proceedings continue. Let's go live to the Sweeney Convention Center.
First of all, to acknowledge my collaborators, students Stephen Shropshire and Xiaowen Fan, who I'm working with presently, and also two other former students, Huajie Zhang and Reinhard Schumann, who worked with me on hydrogen interactions with vacancies in electrolytically charged nickel some years ago at Clark University. Okay. Well, first of all, what is PAC? It stands for Perturbed Angular Correlations of Gamma Rays, and I'll be telling you more about that in a minute or two. One of the foci of this session is applicable condensed matter physics. Well, I can't be sure that it's applicable, but it's certainly condensed matter physics. The question is, where, if anywhere, do fusion processes take place? It could take place in the electrolyte, on the surface of the sample, or just outside, in the bulk of the cathode at ordinary types of interstitial lattice sites for the hydrogen, or it could take place in the bulk at special sites, including various kinds of defects. The defects most relevant are probably grain boundaries, dislocations, or vacancies. Now, it's a fact that hydrogen and deuterium bind quite strongly in lattice vacancies, atomic vacancies, and the perturbed angular correlation technique is useful because we can monitor trapping of individual hydrogen atoms in lattice vacancies next to impurity probe atoms with atomic scale sensitivity. We can also observe multiple trapping of hydrogen atoms in vacancies. The work I'll tell you about focuses on nickel and platinum because we haven't done any work. It's just starting now on palladium. In the next talk by Biesenbacher, you'll hear a discussion by a different technique of hydrogen trapping in vacancies in palladium. So I'll be telling you about hydrogen trapping in vacancies, about formation of nickel hydride, which we believe we've seen in the past, and even potentially palladium hydride. Of course, nickel, palladium, and platinum hydride. Of course, nickel, palladium, and platinum are in the same column in the periodic table, and nickel is a lot cheaper, and its hydrogen metal phase diagram is similar to palladium. And then we've done some very recent measurements on the role of lithium cations, which of course were a common cation in almost all the electrolytes which people have used. Okay. Well, I'll tell you very briefly about the PAC technique. It's a technique which gives you information which measures the interaction between nuclear moments and internal fields in solids, like NMR or Mossbauer effect. And this schematic setup is shown here. If you have a gamma-gamma cascade, a nuclear decay of an atom followed by two gamma rays in succession, it turns out that the direction of emission of the second gamma ray is correlated with respect to the direction of emission of the first. That really means simply that the nuclear spin of the intermediate state is aligned by the preceding nuclear decay, the preceding gamma ray. Well, if this is a long-lived state, then there's the possibility that the nuclear spin of the intermediate state can precess sensibly during its lifetime. For indium-111, the lifetime is of the order of 100 nanoseconds, and so this it can precess through a number of full circles. What one does is to, if you have an external or internal magnetic field, is that the anisotropy pattern will precess with the nuclear spins, and by measuring, by histogramming the time differences between the arrival of a pulse in detector 1, a scintillation counter, and a pulse in the second detector, and histogramming that, you'll see not only the exponential decay of the intermediate state, but it will be modulated by the anisotropy function. So we can extract then that modulation function, which is called a perturbation function, and that will be characteristic of a particular lattice location for the probe atom in a solid. The features of the measurement are that we can measure interaction frequencies. We can also get some information with a counterpole interaction about the local site symmetry, whether it's cubic, has at least an axis of threefold symmetry or lower, and I'll stop there. Now, for the past 7 or 8 years, I've been studying point defects in metals using the following kind of approach, which has been exploited quite a lot in Europe. I introduce probe atoms into the solid by diffusion, and then produce lattice vacancies, such as shown here. Then, well, if the vacancy is far away, then the probe nucleus is not sensible to the disturbance caused by the lattice vacancy. However, if we warm this damaged sample up, and the vacancy moves and traps next to the probe atom, as shown here, then you'll see an appreciable precessional interaction. Right. So we can then use these frequencies, there happen to be 3 Fourier components for a spin 5/2, as a signature, if you like, for a specific lattice location. Okay. Let me show you how that works, this defect trapping in nickel. Right. If you take a piece of nickel, diffuse the indium into it, and then make a measurement, you'll find a very large amplitude, high frequency precessional signal due to indium on defect-free substitution lattice sites. If you then damage the nickel by plastic deformation and then annealing it to a temperature of 400 K, you'll see a reduction in the high frequency signal and the appearance of a low frequency signal. That's caused by trapping of a lattice defect. If we warm this up higher, that defect will detrap and we get back to where we started. Okay. Now, the nature of that specific defect complex, which I just showed you a signal for, the low frequency, is the following. And as shown on the right-hand side of the figure, it involves an indium probe atom sitting at the middle of a tetrahedron of vacancies in the FCC lattice. We know this for 2 reasons. From the PAC signal, we know that the charge symmetry is cubic charge symmetry, and also indium atoms have been observed to move to tetrahedral interstitial locations at the same temperature that we observe the formation of that signal via PAC, by positive ion channeling and also by electron channeling, conversion electron channeling. Okay, now let's go on to hydrogenation. If we use this piece of nickel now as an electrode as a cathode in a little electrolytic cell, we can observe the following kinds of changes in the signal. If this nickel sample was loaded with a 20 milliamp per square centimeter current for about an hour in a 1 molar H2SO4 solution with a little arsenic poison, recombination poison, and as you can see, there's a complete disappearance, an apparent disappearance of the low frequency signal. The reason is that we've trapped at least one hydrogen atom in each one of those cubic complexes, and we've destroyed the cubic symmetry. The result is that you see only the high frequency signal for the substitutional indium atoms, which remains there because the hydrogen atoms do not trap next to the substitutional indium atom. If you then anneal the sample at a low temperature, 320 K, for 15 minutes, you see a partial reappearance of the low frequency signal. And then if you anneal it at 370 K, you'll see a complete detrapping of hydrogen from all these cubic complexes. So you can monitor both the trapping and the detrapping, sort of the localized version of desorption of hydrogen using this technique. In this figure is shown the amplitudes of those signals as a function of annealing temperature. After hydrogenating the complex, the cubic defect fraction falls to 0, and then it slowly recovers as we anneal into the temperature range from 300 to 350 K. We get the same qualitative results for hydrogen and for deuterium. Now, I should say that this kind of detrapping behavior centered around 350 K has been observed in very many samples. However, in one of our earliest experiments to decorate the complex, we used a much higher current density, 200 milliamps per square centimeter, same kind of electrolyte, for hours, and we observed a very different behavior. The substitutional fraction dropped, and the recovery took place, the detrapping, if you like, only took place around 400 K, much higher temperature than the 325 K that we had observed in many other runs. Now, it's also unusual that the substitutional fraction dropped by 30%. We attribute this to 30% of the volume of the sample becoming non-magnetic. Nickel hydride is non-magnetic. And that the hydrogen is retained by the nickel hydride, which probably forms at the surface, until the nickel hydride decomposes, in effect decomposes around 400 K. In other words, we have a sample with nickel hydride at the surface surrounding nickel at the interior. So at the interior, you still have cubic defect-free substitutional lattice sites. This is our evidence for nickel hydride. Now, some of you are aware of the, the phase diagram for hydrogen and nickel is very similar to the phase diagram for hydrogen in palladium. Except for the fact that you have to raise the pressure to 6 kilobars, gas pressure, before hydrogen flows in and you convert from the alpha phase to the beta phase. But at 25 K, as you can see, you can convert at 6 kilobars, you can drive in hydrogen, and before you have to push harder, you can achieve a hydrogen to metal atom ratio of 0.9. So the isotherms are similar to the isotherms of palladium except for the pressure differences. You can produce the nickel hydride by electrolysis. You can achieve a higher hydrogen to metal atom ratio, and therefore this would look like a prospect for trying to observe cold fusion experiments. Okay. Because time is going, I'm going to skip. Well, let me just show very briefly what happens when you introduce hydrogen into platinum metal. Right. Here in the top of the figure is shown the signal for two different vacancy complexes in platinum. This one, the one with the higher frequencies, the orange shown by orange, is a divacancy complex. And if you use an electrolytic bath for 2 minutes, you charge it for 2 minutes, you convert about half of the orange signal to this green signal, which does not have a 1 to 2 to 3 ratio of Fourier components anymore. After 4 minutes, you've converted this entire high-frequency signal to this signal. After 10 minutes and 20 minutes, you get a broadening and smearing of the frequency distribution. We attribute the shift from here to there to trapping of a single hydrogen atom, and then the subsequent broadening to trapping of multiple hydrogen atoms. So the same kind of, it's very easy to introduce hydrogen into the lattice. It traps relatively strongly in these vacancy complexes with binding enthalpies of the order of half an electron volt. And we can also observe multiple trapping. Now, about the role of lithium. In the Fleischmann-Pons recipe, the 0.1 molar lithium deuteroxide solution, you have a 0.1 molar lithium ion concentration, a 0.1 molar deuteroxide ion concentration and a 10 to the minus 13 molar D+ concentration. So one question which a physicist like me can naively ask is, does the lithium plate out? You have a much higher cation concentration of lithium than deuterium. This is, of course, very naive. Lithium is, compared to hydrogen, is an oversized atom. It's got a core, a 1s core, but the ionic radius is fairly small. It's only 0.7 angstroms. So it may deposit like hydrogen or deuterium. It may, in fact, diffuse into the cathode like hydrogen or deuterium, and the rapid diffusion of lithium is familiar in jelly and silly detectors. And it will probably trap more strongly in vacancies than hydrogen or deuterium because of its size effect. So we began an experiment recently to attempt to decorate vacancy complexes in platinum with lithium atoms using electrolytic, using this LiOD bath and LiOH. We expected that we would see a different signal for a decorating a guest lithium atom, and that we might be able to infer something about the diffusion of lithium into the metal sample under these electrochemical charging conditions, where you have a large hydrogen flux. The cell we used was had a platinum crucible to avoid any problems from dissolving stuff into the electrolyte, and a platinum cathode. We've used both a 1 molar and 0.1 molar lithium hydroxide solution at different current densities. For the 1 molar solution, we observed the pH to decrease from 13 something down to 9 something after 24 hours of electrolysis. In other words, all the lithium was gone from the electrolyte. This is with a platinum cathode, of course, not a palladium cathode. With a 0.1 molar solution, after 24 hours, we've removed it and transferred it into liquid nitrogen within 2 seconds after cutting the current. The shiny metal surface turned first light brown and then gunmetal black within about 6 seconds, all of this taking place under liquid nitrogen at 77 Kelvin. Our hypothesis is that lithium had plated out, if you like, on the surface, had concentrated on the surface, and had either reacted with oxygen, which was dissolved in the nitrogen, or with nitrogen itself. Our conclusion is that lithium rapidly deposits on platinum. We have not seen any evidence of lithium trapping yet, although we're still looking, and we do see a growing signal at long times, which may be due to platinum hydride. As you may recall, yesterday Professor Bockris referred to the fact that lithium does plate out on platinum, so that's not perhaps unexpected. In summary, I've tried to show you that PAC is a technique which can give you local information on hydrogen in metals near impurity probe atoms at very high dilution, I might add, information on the hydrogen binding in vacancies, and on phase transitions in the case of nickel hydride. For the future, we realize that we may be able to, in certain cases, to use this technique to deposit lithium in an unoxidized form on metals, and perhaps to introduce it for purposes of diffusion. Now, finally, if fusion were to take place in lattice vacancies, for example, by pressing many atoms into a vacancy, we would then be able to detect the complete disruption of the vacancy complex after the fusion event, because the atomic collisions would knock atoms out as they're exiting in opposite directions. And we're just now beginning experiments on to study vacancies and hydrogen trapping in palladium. Thank you.
We will take a couple of questions, for time is very short here, please.
George Erickson, Los Alamos. The case where you hydrided for a matter of minutes, the nickel.
I'm sorry.
The case where you hydrided for a matter of minutes on the nickel, what was the thickness of that nickel sample?
The thickness was of the order of 2 mils, and the probe activity was distributed uniformly throughout.
Thank you.
Alan Bard, University of Texas. We've been also looking at lithium and palladium, but I can't believe that you're getting lithium deposition under your conditions on platinum. If you look at the potentials to deposit lithium. If you deposit lithium as the metal, you're at around minus 2.7, at least in, if your activity is close to 1. It's conceivable you're depositing lithium hydride, which is at much lower potential. But even that is quite negative. I would say about minus 1.4. So it's very hard to believe you do that. The other thing I can't understand is the pH change. I mean, it seems to me impossible to get the pH down by total lithium deposition. Is this cell under a nitrogen atmosphere or something?
No, it's under air.
So my guess would be you're absorbing CO2 from the air and getting carbonate formation, and that's bringing the pH down.
That's possible. That may be possible. We haven't thought of that. As far as the lithium deposition goes, we're undertaking a neutron activation analysis to detect quantitatively the amount of lithium which has been deposited on one of the samples. Lithium-7 goes to lithium-8, which has a 0.8-second half-life, but if you use a rabbit system, you can do neutron activation analysis.
I think your technique is very interesting, very new and exciting. I'd like to point out, however, that probably for fusion, it's more important to note another kind of trap which occurs when you put hydrogen into metals, and which has been well studied, particularly in iron. You actually get quite substantial voids, about 1,000 angstroms across. These fill with hydrogen. This is the part that electrochemists have always calculated with a very, very high pressure. So what you want to look for, and what I think is most interesting with fusion, is not actually the atomic vacancies, which may fill with 1 or 2 hydrogen atoms, but the vacancies where you could talk about H2 formation. That's where the high pressure will occur.
Yes. What you've said is perfectly right. However, first of all, for those of you who are deforming your palladium, the lattice vacancies will not anneal out unless you anneal the thing at between 400 and 500 K. Right, so they will be in your sample, and there will be lots of them if you deform it, of the order of 1/10 to 100th of a percent atomic fraction. So they're certainly there, and so the question is, and in the next talk you'll hear about trapping of many hydrogen atoms and how that's possible in a vacancy.
There's one last question, please.
Is it working? Tani Hata from RIKEN. About the deposition of lithium. Our analysis says that it's not a deposition surface, but the diffusing into the palladium. And what we observe is it's really diffused into at least 2 microns. And its distribution is almost flat. So my guess is that the lithium is really diffusing into palladium after electrolysis, more than 2 microns.
Thank you for your comment. I meant to mention your work on palladium, lithium diffusion into palladium. Yeah.
There's one question, Dr. Barnes. Yes, very urgent. In the really last remark.
Barnes, Caltech. XPS is not a particularly sensitive method for looking for lithium. However, we did study our samples after large numbers of hours, and deuterium to palladium loads at over 0.7. And our measurements indicate that within the first 30 microns, which is the sensitive depth of the XPS, we have an upper limit of 2 atomic layers of lithium.
Okay. I think we have to proceed now to the next item. I would like to call for Dr. Bessenbacher from University of Aarhus, Denmark. It's a lecture by Dr. Bessenbacher, Dr. Nielsen, Myers, Nordlander, Norskov on interaction of deuterium with lattice defects in palladium.
Let me again mention my co-workers. It's Brian Bech-Nielsen from University of Aarhus in Denmark, Sam Myers from Sandia National Laboratories in Albuquerque, Jens Nørskov from Technical University at Lyngby in Copenhagen, and Peter Nordlander at Rutgers University. What I'm going to tell about is a continuing effort where we, by means of ion beam analysis and ion implantation, is pursuing a more general and quantitative understanding of the interaction of hydrogen with defects in metals. And from an interplay between theory and experiment, I think we have obtained a fairly simple picture of describing both quantitative and also qualitative a vast number of experimental data, such as, for example, the trapping of hydrogen to defects in metals, which I'll discuss today, but also properties concerning hydrogen interstitial position in metals, such as heat solution, and also properties of hydrogen at metal surfaces. The theory by which I later will compare the experimental data, is the effective medium theory, which is developed by Jens Nørskov and co-workers. And the basic idea is that you replace the host with an effective medium, which is simpler to treat theoretically, but which is physically representative. And the theory is an effective medium theory where the effective medium is a helium or homogeneous electron gas. And I will not here have time to go into the detail with the theory, but just remind you that the embedding energy, and that is the energy of the combined hydrogen metal system minus that of the isolated hydrogen and metal system, can be written as a sum of 4 terms here. The first term here is by far the dominating one, and that's a term which is fairly simple. It only depends on the interstitial electron density. Then we have a second term here, which is a hybridization or covalent term, which describes the interaction of the hydrogen with the metal d bands. And then we have 2 smaller terms here, which I will not discuss today. If you look at the first term there, which only depends on the interstitial electron density, that can be calculated once and for all for a given impurity. And of course, in this context here, we are mainly interested in hydrogen. And curve is shown here, the embedding energy as function of average interstitial electron density in atomic units. And you can think of this curve here in a fairly simple way. If you consider a hydrogen atom coming from infinity and approaching a surface, for example, then it goes through a chemisorption minimum, and then the energy increases as function when you're forcing the hydrogen atom further and further to the surface. So this increase here at higher electron density is nothing else than when you press the hydrogen into a metal atom, then the hydrogen 1s state has to orthogonalize more and more electron state in the metal, which then causes energy or gives rise to an energy increase here. The minimum here is explained by the fact that you gain energy by transferring electron from the electron gas to the affinity level of the hydrogen. It's such a simple curve here you can understand fairly. You'll see as I go on, you can understand many things what goes on in hydrogen metal system just from this curve here. Let me point out that the second term there, the hybridization term, which was the interaction with the metal d band, is proportional to 1 minus f, where f is the degree of the filling of the d band, meaning that for copper would have a full d band, it's essentially 0, and then it increases to the left in transition metal series. And for example, if you look at chemisorption of hydrogen outside a metal surface, you would say here in principle that every hydrogen outside a metal surface can find a position corresponding to this minimum here, and then you would have the same chemisorption energy for all the metals. That's of course not true. But we had also had the other term down here, which was proportional to 1 minus f. So if you now plot the chemisorption energy experiment and theory, then you see that the chemisorption energy increases to the left in the transition metal series. And there's a very good agreement between experiment and theory. And this increase to the left is nothing else than this 1 minus f down here. Also, the heats of solution are very nicely reproduced by this theory here. Let me then go to our experimental studies. And I said that was a combination ion beam analysis technique and ion implantation techniques where we had tried to pick out certain conditions which is fairly easy to understand, so we can extract trap binding enthalpies and information of where the hydrogen is sitting in certain lattices. What we normally do is that we implant deuterium at low temperatures at an energy of the order of 15 kiloloctane volts, which ends up at a range of the order of 1,000 to 1,500 angstrom. Then we probe the deuterium with bombarding the crystal with 750 kV helium-3 ions, which gives a nuclear reaction, and we then detect either the protons or the alpha particle with a solid-state detector. You can see as long as the helium-3 ion is losing energy in the crystal, the nuclear cross-section decreases here, and you can see that we essentially probe hydrogen within the first half micron with this technique here. You can also see that the analyzing beam is ending up at a range in here of the order of 1 to 1.1 micron. In some cases, we also pre-implant our crystals prior to the deuterium implantation with 25 kV helium, typically at a fluence of the order of 4 times 10 to the 16. Before I'll show you some annealing curves for deuterium, I'll show you some for nickel, because they are maybe easier to understand. So what I have plotted here is the fraction of deuterium retained in the lattice, normalized to 1. We have implanted deuterium at low temperatures. Then we anneal up the temperature at a linear ramp with a rate of the order of 1 to 2 K per minute. And we then continuously probe how much hydrogen is left in there, and then we get some annealing stages up here. The first thing you can see is that all these annealing stages are well above that curve here calculated for the case of no traps available, where we have perfect lattice diffusion out of the crystal. So we are associated with hydrogen trapped at defect sites up here. The strongest traps we have observed is in the case where we pre-implanted with helium prior to the deuterium implantation. That is creating a dense array of helium bubbles in our crystal, which has been observed with transmission electron microscopy. In the case where we only implant with deuterium, we see, okay, I should also say right away up here that this state is then associated with hydrogen trapped to the internal walls of these bubbles there with a mechanism similar to chemisorption on the surface. The second state here, where we only implant deuterium, we associate with hydrogen trapped into vacancies. And you can then see that we get a lower temperature stage down here if we increase the amount of deuterium implanted. And that is in fact associated with multiple occupancy of a given vacancy. The way we extract binding energies here is that we model all these release curves here by a diffusion calculation, which take proper account of trapping and retrapping from the traps. We include the known hydrogen diffusivity, we include the vacancy and the interstitial mobilities, and we include a vacancy and interstitial annihilation, and also the multiple occupancy of the traps. And we then get trap strengths, which are listed here for nickel for 0.55 for the bubble traps, 0.43 for the vacancy trap, and 0.24 eV for the multiple occupancy if you have more than 2 hydrogen in a vacancy, all reference to a solution site in the lattice. If I now show you some results for palladium, they are in principle similar. We again see that the highest trap strengths we observe if we pre-implant our samples with helium. We see lower states here if we only have deuterium implanted. And again, if we increase the amount of deuterium implantation, we get a lower state here. Again, exactly the same as we saw for nickel. The reason with palladium why it's slightly more complicated than nickel was that in the nickel case, the surface is permeable. So when you start to have release from the defect traps, the hydrogen goes to the surface, recombines, and goes into the vacuum, desorbs. However, in palladium, it turns out that when we have release from the traps, the surface is still impermeable. So the way we actually extract trap strengths here is then we have the strong helium traps introduced by the analyzing beam, and we then see a redistribution from defect traps in the near surface region. We then go to strong traps at deeper depths around 1.1 micron, which we not probed in the beginning with the analyzing beam, and that is causing this behavior here, but I will not have time to go into in detail. But qualitative, they are very similar. If we now show the trap strengths we have extracted here for a number of different metals and compare that with the effective medium theory, the first thing you can see is that that's for hydrogen at a single hydrogen at a vacancy, and that's for hydrogen bound to a void up here. We can see that the theory is capable of reproducing all the trends observed, and even there's a very good absolute agreement, which is maybe a little bit surprising. One thing was very evident here is that palladium has fairly low trap strengths. How can then one now understand this? That's again fairly simple to understand qualitative from this curve here, because as I said, the trap strengths are measured relative to a solution site, and an interstitial solution site is lying on this linear part here. That means that any dilution of the lattice, a given trap with a given low interstitial electron density would give a trap. You have the trap strength then relative to a solution site up here, and then the trap strength, for example, for a vacancy, which has such a low interstitial electron density that we acted down to the minimum here. Actually, the interstitial electron density in the vacancy is to the left of the minimum, implying that hydrogen will not sit at the vacancy, but rather being displaced somewhat away from the vacancy. The palladium had a large lattice parameter, thus a low interstitial electron density, and thus the soluble site is lying closer to the minimum here than, for example, it is in nickel, and thus you gain less energy by going from a solution site to the vacancy, and that's the reason why the low binding energy is in palladium. On the next curve here, I have shown the results for multiple occupancy of a given vacancy. If you have a vacancy, then in an FCMC metals, you have 6 octahedral sites, which is around the vacancy. And what's the dots here are then the results from the calculation, where we then have tried to put in 6 hydrogen in a certain vacancy. What turns out to be is that, and all the trap strengths here are now measured relative to that for only a single hydrogen in a vacancy. But if the next hydrogen you put in the vacancy, that is just lying on opposite here, so there will be little interaction between these 2 hydrogen atoms. But then when you start to fill the other hydrogens, there will be a hydrogen-hydrogen interaction, which then is giving rise to a decrease in the binding energy here. But that's again easy to understand within this scheme here, because what it matters is that the other hydrogen is donating electron density to the certain hydrogen you're looking at. And that means that you move from the minimum up here along this curve, and then your gain in energy, the trap strength here, is decreased. So you see that the trap strength of the last hydrogen in the vacancy is lower than that for a single hydrogen in a vacancy. The solid lines here is in fact the results from the experiment. We could not in the experiments model 6 different binding energies. So what we did was we said, okay, there's one binding energy for 1 or 2 hydrogen in a vacancy, and then there's another binding energy for 3 to 6 hydrogen in a vacancy. And you can see that qualitatively there's agreement. We see the decrease in binding energy, but the agreement is not as good as it was for the vacancy, and there's good reasons for that. One thing again we can point out with the palladium is that palladium is probably the system we have studied so far where it's most energetically favorable to have many hydrogen in a vacancy. Okay, so to summarize the content with the vacancy trapping, we can say that any dilution will lead to a trap. A small dilution you find for a dislocation or an interstitial atom, and thus you have a low binding energy of the order of 0.05 or something like that. 0.05 electron volts. For self-interstitial, which has larger relaxation volumes, you see somewhat stronger traps that we get of the order of a tenth of an eV, and the strongest traps you have for vacancies are voids. And in fact, for palladium, I've here made a list of the trap strengths which we have observed experimentally. That was 0.3 eV for the void and vacancy clusters. It's 0.23 eV for the vacancy, and it's 0.15 eV for multiple occupancy of the vacancy. Now, concerning the detailed lattice position of the hydrogen. Fine. Then we have used the ion beam analysis again combined with a well-known channeling technique, and I have not time here to discuss the channeling technique, but I hope some of you at least know what I'm talking about. What we've done here is that we implant deuterium at low temperatures and then measure the well-known channeling technique around the 110 axis for deuterium and palladium. Along the 100 axis, the octahedral side is shadowed, and that means that we see the characteristic channeling dip for the deuterium, implying that hydrogen deuterium is sitting at the octahedral interstitial site at low temperatures where there's no mobility. Then we start, and I should also say that this narrowing here gives of a root mean square displacement amplitude of hydrogen in a vacancy, which is 0.25 angstrom. Then you start to anneal up, and if isochroning anneal 15 minutes at a certain temperature, you then cool down again and measure low temperatures. And you then start to see when you come up around 50-100 K here, the hydrogen starts to be mobile. It goes to the strongest traps, which is the vacancies. And at the highest temperature here, we have all the hydrogen associated with vacancies. We then see a narrow dip, and superimposed to that, we see a flux peak here. That can be analyzed in the way that the narrow dip here is some part of the hydrogen is sitting in an octahedral site displaced 0.3 angstrom away from the octahedral sites towards the vacancy, and some part is sitting at a site close to a tetrahedral site. If we now go back to the theory and see if we can understand that, then I've here shown the potential from the theory along 2 different cuts along the crystal here, one along the 100 plane and one along the 110 plane. And if you then take this potential, solve the Schrödinger equation, get the wave function and the ground state density, we can see that there is in fact a maximum density for the site displaced away from the octahedral site towards the vacancy, which is sitting in the middle. However, that could not, we had also this tetrahedral component, which cannot be explained by the ground state here. But in fact, what turns out is that we also have excited states of hydrogen sitting in a vacancy. And these excited states are in fact more tetrahedral-like. So the way you can think of this here is that in fact when hydrogen is trapped at a vacancy, there is at least 25 Kelvin where we are measuring. There is in fact a population between the ground state and the excited states. I should now point out that if you now try to put more hydrogen into the lattice, this delocalization behavior, this excited state here disappears. And if you, for example, come to a situation where you have 3 or 4 or even 6 hydrogen in a vacancy, they will sit very close to an octahedral site, which also is the case for the hydride, which also has been measured a long time ago with neutron diffraction studies. So I hope with this talk here I have shown to you that we have a fairly detailed understanding of the interaction of hydrogen with metals, and we started vast number of metals so far, and this theory can explain not even the qualitative trends, but also give a fairly good absolute agreement. And if some of you are interested in that here, we would like you to give you some preprints of what we've been doing so far. Thank you.
Well, very nice lecture. Any questions or comments? Yes, Dr. Morrison.
Thank you. Morrison, CERN. I wonder if you'd like to answer some of the questions we've all been asking, such as, what is the chance of having 2 deuteron nuclei close together?
0. I mean, it's very energetically favorable to have 2 hydrogens sitting on octahedral sites. I mean, both the theory gives that, and also, we could see that with the experiment. So 0 is the answer.
Okay, thank you. I think it's very nice to have a very clear answer. Secondly, what is your opinion of the possibility of fusion?
Shall we vote on it?
Your last answer was very clear.
$100 answer. Well, I'm skeptical.
I think. Any more serious comments or questions? Yes, down there, please. Microphone.
Hubert Chuan from Princeton University. I wonder if you could comment about something for us who are not in this field, that is, for those voids to develop, and is it possible that the exothermic reaction of just atoms, just deuterium atoms, go together into molecule and release sudden bursts of energy?
I mean, it's very hard for me to say, but I mean, one comment I would make is that, I mean, if you were interested to creating bubbles of hydrogen, where hydrogen is sitting in molecules, I mean, you should by no means choose these exothermic metals like palladium, titanium, whatever. I mean, if I was going to look for hydrogen bubbles in the metals, I would choose aluminum, which we have been studied, where we have, in fact, together with Sam Myers, seen hydrogen bubbles. And copper is another well-known system. And the reason being that for both aluminum and copper, there is a very low solubility, and therefore the hydrogen segregates to bubbles, which would never happen in these hydride-forming systems. So, I mean, if you are interested to bubbles, where you have maybe hydrogen molecules sitting there, which is probably the closest distance you can come to a metal lattice, I would choose a system like aluminum or copper.
Yes, could you tell us what the highest stoichiometry? Yes, Dr. Bush from Cal Poly. Could you tell us what the highest stoichiometry that you've studied in the palladium-deuterium system is?
The palladium?
Palladium-deuterium system.
Yes.
What's the highest stoichiometric ratio that you've studied?
Well, we have been studying it with the ion beam techniques, and we get this 0.7, 0.8 hydrogen per deuterium.
Well, we've already heard in this conference that is probably marginal for seeing any of the effects we've talked about.
Yes.
So what would your comment be on that?
But I mean,
what I'm saying is that people who claim to have seen results are talking about stoichiometries much higher than what you've studied.
Yeah, but I mean,
so I think your claim
to be able... I think that's Alice in Wonderland again. I mean,
I think your claim to be able to comment on that at all is very tenuous. That's my comment.
But I mean, we have measured with this ion beam analysis technique. If we were taking thin foils there and measured, I mean, we have done electric analysis and also charged it from the gas phase, and we have done DC glow discharge, and you come up with this 0.7, 0.8 deuterium palladium. So, I mean, what more to say about
that? My name is Fred Rothwarf. I'm with the Center for Innovative Technology for the state of Virginia. We're dealing here with a very non-equilibrium situation when you're dealing with the evolution of heat, the occasional bursts of neutrons and so on, and it seems to really correlate with the microcracking that takes place in such systems and can take place over an extended period of time. For instance, in rare earth metal magnetic materials, the microcracking is used to pulverize these materials. So you're into very fine particles of micron-sized particles. So you're dealing essentially with the binding energy of the lattice disrupting the, being released with the disruption process. Now, it seems to me that one could obtain acoustic emission signatures of these events, and people could try that in a variety of experiments that they're doing, either electrolytic or gas cells. And with that acoustic emission, you may well be getting the emission of high energy compressive solitons, which can dramatically put you into a non-equilibrium situation where an occasional fusion event might be possible. And certainly the microcracking can account for the long-term emission of energy in these various electrolytic cells.
But I mean, one comment about the non-equilibrium situation. I think in the next talk we're going to have a very nice situation of a non-equilibrium talk where by means of ion implantation you can actually create supersaturated deuterium-hydrogen ratios, as Myers will show in the next talk, which we also have been studied. If you implant deuterium at low temperatures, you get actually supersaturating. But I mean, Sam will tell you about that in the next talk. So this 0.8 before I measure, that is an equilibrium. And I think he'll come up with a higher number, but that's in a non-equilibrium situation where you force the deuterium in by ion implantation.
Please try to stay to the subject of the lecture. Next, Dr. Bockris, please.
As far as the voids are concerned in palladium, there is a poster upstairs under the name of Fuller, and this poster shows actual photographs of the voids and shows that they burst. They burst out into blisters and with very considerable energy, and also this then gives rise to a number of dendrite formations around the edge. And I think that as far as the curious phenomenon, the non-equilibrium phenomenon we're talking about are concerned, this may be very important. In respect to the ratios, the highest I've ever heard of is 1.1. But whether that's to be interpreted as in terms of stoichiometry, or whether that includes the enormous amount of hydrogen that you hide in the voids, I don't know. Perhaps it includes the voids.
But I think Sam Myers in the next talk will show you 1.3. Is that right, Sam?
Yeah. There's one last question here.
Nate Hoffman, E-Tech, Rockwell. Question with respect to an actual microstructure. When you put the deuterium into the palladium, you get regions that are highly distorted surrounding regions that aren't very distorted. And that same Fuller paper, which I think is back there, shows very nice metallography of these regions that are highly distorted and the within regions that aren't distorted at all. Does your theory take into account this sort of behavior within a single grain?
If I can find it here, then I mean, the way, I mean, which is also well known, has been studied among other things by a neutron diffraction technique, is that, I mean, if you, for example, increase the occupancy of the hydrogen in the metal, if you go up to a hydrogen deuterium ratio of 1, then you get an expansion of the lattice of the order of 8% or something like that. I mean, that's well known and has been measured. And I mean, that's come out with the theory here.
But it's along certain crystallographic directions that you get it.
Yes.
It's not uniform within the grain. It's almost like a spinodal decomposition structure you get.
Well,
you have to settle it, I guess, in private. Yes. We have to thank Dr. Bessenbacher for a very nice lecture. Next is Dr. Myers, a paper by Myers, Vollstedt, Schreiber, and Richards. Dr. Myers from Sandia National Lab. Search for cold fusion in superstoichiometric palladium deuteride using ion implantation. Please.
Well, I'd like to discuss some experiments in which we have searched for cold fusion in palladium deuteride that was formed by ion implantation of deuterium at cryogenic temperatures. Our motivation in using this rather unconventional way of forming the deuteride was that it is capable of introducing deuterium to palladium atomic ratios substantially greater than 1. As a matter of fact, the saturation behavior of implanted deuterium in palladium at cryogenic temperatures was investigated about a decade ago by Muller, Bessenbacher, the previous speaker, and Bödiger at the University of Aarhus. And using very detailed nuclear reaction profiling methods, they found that if you implant to saturation at low temperatures, the key being there that the deuterium diffusivity is very small, so it isn't mobile once you inject it into the lattice, that one reaches atom ratios of about 1.3 to 1. So our experiment then basically consisted of performing low temperature implantations to achieve these high stoichiometries, and then using a charged particle detector to look for the energetic particles from DD nuclear reactions. Of course, as has been apparent from this conference, when one uses high pressure gas phase charging or electrochemical charging, these higher atomic ratios, in particular atom ratios above 1, are not easily achieved as they are with the implantation. Our experiment is outlined here at the bottom. We began by ion implanting 10 kilovolt deuterium from an ion accelerator into palladium, with the specimen being held either at 40 or 80 Kelvin. The implantation was carried to the point of saturation. During the implantation process, we monitored the buildup of deuterium within the metal matrix by actually using that charged particle detection system to observe both energetic protons and tritons from the